Okay. Otherwise, it will be on the record. Okay, class. Those who are in Zoom, can you see the screen? Okay, good. So what we will do today, all of you should have one class lesson 15, one class example 8, and one copy of this one. All of you have that? You can get that from there, from that front row. Okay. So what we will do at the beginning, we will, or you will write down on your class lesson 14 because we didn't cover everything. And I will tell you when you have to move to class lesson 15. Okay. Okay. So what we did last week, we tried to understand what will be the pressure distribution for different type of surface, right? So it can be vertical, it can be horizontal, it can be inclined, and it can be in any shape based on what we are dealing with. So it can be anything. So what we will do, we will try to understand what will be the pressure distribution on each type of surfaces. And we did that, this one in our last class. So let's start with this one again. So for vertical water surface, vertical plate and horizontal plate, let's draw the pressure distribution again. So this is the water surface, so that is 0. And here, if I just use any arbitrary number, 3, 5 or something, if it's 3 feet, that is the 1. So at this point, pressure is what? 3 gamma, right? And we also know on horizontal surface, there is no pressure variation. So at any point, pressure will be 3 gamma, right? And for the vertical one, again, it's 0, 3 feet. And the pressure here is 3 gamma. But this time, pressure is changing at different level. So the pressure distribution will be something like that. And we all practice up to this point in our last class, right? Any question up to this point where we stopped? Are we good up to this point, everyone? Okay, so that was the vertical one. Now, we will do a little bit more discussion on this vertical one also. So on your copy, you don't have all of these lines, you just have a straight line here. So what I will do, I will just zoom that so that you can draw on your copy. And you can see, we just discussed that pressure distribution, the triangular one. For the right picture here, like in this point, once we have the pressure, we need to know the force also, because that is the main thing we are calculating. And for any force, you need to identify the location on which that force will be applied, right? So that is the location here. And to find that location, we need to use your statics knowledge. Again, with that center of pressure, centroid, moment of inertia, those type of stuff, we will use that here. So just to let you know, only for this part, we will find the location of the force also. Okay. Since this is a triangular one from your, if you can remember where will be the location, it is actually 1/3 from the highest load or 2/3 from the lowest load. But we will calculate that. Okay. Are we good with this one? Okay. Just draw the specific, like the shape and the location. You don't need that much details. Okay. So once we are done with the simplest case, for this one, what is the difference of with this one, with the first one? Here, that is the plate here. This is the plate. Okay. And this is the water surface. And again, the pressure distribution is same. But is there any difference on the pressure on the surface, like on this plate? Is there any difference there? What do you think? Do you have that one on your copy or? Okay, you have that. Okay, good. So, tell me, what is the difference between this one and the one we just discussed? I'm giving you one hint, the position of water surface with respect to the plate. So what is the difference? Now tell me. Exactly. For this one, you see the water surface is with like the plate pressure distribution on this plate. It started from here, but here that is the pressure water surface is here, but the plate is here. So if I just draw that a little bit separately here, this is the water surface, and I'm just using some arbitrary number. Pressure is 0 here. Maybe pressure is 2 gamma. Here, pressure is 5 gamma maybe. So the pressure distribution on this plate will be okay. So the main difference between these two, for this one, loading shape was what? For this one, the pressure, I'm calling pressure as a loading. So what is the loading shape here? Triangle. And for this one, loading shape is what? Trapezoidal. Yes. Okay. So obviously for triangular and trapezoidal load, the resultant force will be different, but it's important to know what is the load distribution we are getting, right? And for this one, that will be the F. Okay. Now that is one phase, which is the vertical plate. The next one is obviously if we have any inclined surface. Okay. So that's what we will do for the next one here. So let's start with the simplest one, then we will move to the this bottom one. So for the first one, if that is the water surface and that is the plate, okay. So again, pressure is 0 here, and maybe if this is again 3 feet, 3 gamma here, right? And what will be the pressure distribution? If you draw that, this one, right? Now, at this point, pressure is 1 gamma. At this point, pressure is 2 gamma. And at the very end, pressure is 3 gamma. Now, this time we have inclined plate. We know the pressure exactly at that point, which is 1 gamma. But tell me one thing. Do you remember when we defined pressure equals to force times area? This force will be in which direction on the area? Perpendicular or parallel? The F will be always perpendicular to the area, right? So exactly in that way, we know the magnitude is 1 gamma, but the direction will be what? Perpendicular to the plate. Okay. For this one, again, we know the magnitude, which is 2 gamma, but the direction will be perpendicular to the plate. Similarly, for the last one, for 3 gamma, the direction will be perpendicular to the plate. Okay. And now this is the pressure distribution for the inclined plate. Still it's triangular, but just the inclined one. Okay. Now the main thing is you will get the magnitude vertically. Okay. That will give you the magnitude, and the direction will be what? Perpendicular to the surface. Okay. So this is important to know to get the pressure distribution. Now, are you seeing this picture here? Again, this one is inclined. The only difference is the plate is not starting from the water surface, right? There is a little bit distance between the water surface and the plate, right? So if I just separate this one again, this is the water surface and this is the plate. Can you tell me what will be the pressure distribution, like what will be the shape of the pressure distribution on this plate? Again, triangular or some other shape? It will be trapezoidal. You can see that from here. So from this point, if I say P equals to 0, P equals to 2 gamma, and P equals to 5 gamma. So from this point, it will be P equals to 2 gamma, and from this point, it will be P equals to 5 gamma. And you add that. Okay. So let's write down what will be the loading shape. Loading shape is trapezoidal. And what is the loading shape here? For this one, what is the loading shape? Triangular, yes. Okay. So now you can find whether it will be triangular or it will be trapezoidal. It will depend on the position of the plate with respect to water surface, right? You got that idea? How can you find that? So again, you will get the magnitude from vertically gamma h, and then you will just place that force of that pressure perpendicularly on the surface, right? Are we good up to this point, everyone? Come back. Are we good? And you can see the board properly. Okay. Good. So the last one, this time, if we have something which is not vertical, which is not inclined, rather it can be any shape. It can be circular, it can be any arbitrary shape or something. But the main thing is same. You will get the magnitude by P equals to gamma h, and you face all the force or pressure perpendicular on the surface. So let's do that. Here, this is a surface here which has a circular thing, and here it is 3 feet, and maybe the diameter of this one is 2 feet. I don't know why I'm using 3 feet all the time. It's just arbitrary number. Okay. So the what will be the pressure distribution here? P equals to 0, P equals to 3 gamma, P equals to 5 gamma, right? This one. Now I need to know what will be the pressure distribution on this surface, or what it will look like. So that's what I will do now. That is actually the pressure on this side, right? Here the pressure is 3 gamma, and here pressure is what? 5, yes. Now we will get all the magnitude from here, and we need to place that on this surface. So what we will do, I will just use this one as 3.5 gamma, 4 gamma, 4.5 gamma. Okay. Can you see from the back? I use a little bit smaller font. Okay. So let's place each one. So for 3 gamma, this is the magnitude perpendicular on the surface. For 3.5 gamma, again a little bit bigger than the previous one, but perpendicular to the surface. For 4 gamma, a little bit bigger than the previous one, but perpendicular to the surface. 4.5 gamma, this one. And with 5 gamma, this is the one. So the final shape we are having is that weird shape of that pressure distribution. Okay. And if you want to calculate the resultant, that will be somewhere here. I don't know where it will be. SR. Okay. Now, obviously, you can imagine to calculate this force, resultant force, it will be difficult. Integration is the way when you can do that. There is another way you can get the resultant force. I'm just giving you one hint, and let's see if you can come up with that. When you have an inclined force, is there any way you can divide that inclined force into something? If there is an inclined force, what is the way you can resolve into, like, how can you solve that? Do you remember horizontal and vertical component of something? Okay, I'm reminding you. If you have something inclined, you can always divide that into horizontal and vertical component, right? So that's what we will do here, just in an opposite way. We will find the horizontal and vertical components, and then we will calculate the actual force or resultant force. Okay. So what we will do here, since this is the horizontal surface, all of this pressure here, can you tell me what will be the magnitude of pressure here at this point? 3 gamma, right? And on this side, it will be equals to 3 gamma, equals to 5 gamma. So you will use, this is the horizontal force resultant. This is the vertical force resultant. How can I find the resultant force? Square of, okay, so this one, right? So for curved surface, Most of the time we will do that. We will calculate the horizontal surface and horizontal force and vertical force, and then we will find the actual resultant force. Okay. Now, for any force, you need to know the location. We already discussed that, right? So, how can we get that? We will discuss that part. And from this point, you can move to your class lesson 15. So now you can move to your class lesson 15. Okay? So move to that point, class lesson 15, and we will try to get an expression for this force. Okay? Now, for today's class, most probably last 10 minutes, we will do some mathematical problem. Other than that, we'll just do all the derivation and everything. So please bear with me. Don't sleep. Okay. Let's start working on that. So there are few available methods how you can calculate the force. I personally like the geometrical method most, but then I thought in your SE manual, they actually covered the formula method. Okay. So you all know that you have to take the FE, right? Okay. So then I thought maybe it will be better if I cover the same method so that you'll get some advantage when you start working on that. So that's why I will use the formula method in the class. But in your textbook, they explained all of these three methods. And for your homework, for your test, I don't care which method you are using. You will get full points if you get the correct answer. Okay. But as a class example and everything, I will cover the formula method. And that's when we need this topic. All of you have that, right? Okay. So for formula method, for doing that, I will derive the equation for incompressible fluid. Give me one example of incompressible fluid. Water. Yes, water or any type of liquid, that is the incompressible fluid. Now give me the characteristics of incompressible fluid. From the name, you will know what is the characteristic. It's incompressible. Volume can be changed, like you can't compress that. Mathematically, we can say gamma is constant. That means gamma equals to weight over volume. And this volume is constant. And that's why it's incompressible gas, right? Okay. And for incompressible gas, since gamma is constant, the pressure variation will be what? Gamma H. We will need that for the derivation. Okay? Now, at the end of this topic, not today, but when we'll be done with this topic, we will discuss briefly how can we get the resultant force for the compressible one as well. Okay. Okay. So, since you have a black and white copy, maybe you will not be able to get the full idea of that picture. So basically what is we are having here, this is the water surface, okay? And this brown one, this is a surface, inclined surface here. So this is the longitudinal view here. This is the water surface and this is the plate here, okay? And we are trying to find what will be the expression for the force. Are you seeing here there is a small area dA, and on that dA there is a force dF. Are you seeing on your copy? Okay, so I will write down few things here. P equals to gamma H, F equals to P times area. Okay, I need this. Since I want to find the resultant force, that will be integration of all the smaller forces, right? Bf. And since I'm using the incompressible fluid, I will at first write down the general expression P D A. And for P, can I write down gamma H D A? Can I write down that? You already know that, so I will just use that. Now from this picture, are you seeing H and Y both here in this picture? Can you tell me what is the difference between H and Y here? H is what and Y is what? Both of them are kind of giving us some sort of depth or distance, right? But Y is what? What H is what? Exactly vertical, right? The H, if you look at the H, this is direct vertical depth. And what is Y? Parallel to plate, or we can say like across the plate. Yeah, parallel to the plate is a good word also. So this one is vertical depth. Okay. And Y is, just write down Y is maybe depth across the along the plate. Okay. Since both of them are some sort of depth or distance, I can actually write down a relation between that, which is I remove everything. So I will just write down the very final one. Okay, you have that, right? In your copy. Good. Okay, so H equals to Y sine theta. Now one trick question. If the plate is vertical, what is the angle between H and Y? If the plate is vertical. If the plate is something like that. What is the angle? 90, yes. And sine 90 equals to? 1. And that will tell you that when you have a vertical plate, H equals to what? Y, because sine theta equals to 1. That means in that case, you will not have 2 depth, that time you will have 1 depth. And that's why we are using this expression so that you don't have to worry about, okay, what will be the expression for vertical one? What will be the expression for the inclined one? This is a general expression. As long as you know the magnitude of angle, you can get the value. Okay. Okay. So let's write it down. Can I take the gamma outside of that integration sign since it's constant? Okay. So HDA DA, that should be DA. Okay. Now here, YDA is actually the moment of area about the x-axis, which can be replaced by, if you integrate that, what you will have finally? If you integrate dA, what is the final result? Total area A, right? Okay. So you will get y bar A, where y bar is the distance from the x-axis to the geometric center of the area. Okay. So I will write down the next line here. If R equals to gamma y bar sine theta A. And since y sine theta equals to h, instead of that, can I write down this way? Gamma h bar A. Can I write down that way? So I spent a little bit time on this derivation just to show you that this equation can be applicable for vertical one and the inclined one as well, because that is the general expression. Okay. Okay. So I'm moving to the next slide. I hope you are done with that. You're done with that, everyone? Okay. So since the depth of the centroid, here it will be h sine theta gamma h bar A. Of force on submersion. And I think in your copy, you have all the names for each parameter, like which parameter represents what. The only thing just to add on that one, just make sure you write down that h bar is the vertical depth, okay? And if we need something with any other direction, this is the vertical, and if we need something with other direction, that is the direction, okay? So you don't have those two words in your copy, make sure you write down that, okay? Now, once we know the resultant force, what is the next step? Where this force will be applied, the location, right? So, again, your statics knowledge, how can we find YP, XP and everything? Do you remember the parallel axis theorem a little bit? Okay. I know you can't remember the whole things. That's okay. So this is the equation, and are you seeing here that y bar, I bar x and everything? You will get that from this copy. Okay. So there is no title for this one, so I will just write down FE manual statics table. Okay, so this is the FE manual statics table. Okay, and one more thing, this YP, XP, it will depend on surface shape. Okay, so if you have a surface which is rectangular, you will go into this part. If you have a circle surface which is circular, which one you will use? Second page, the circular one, right? So this is important, and this is the YP, and the next one is XP. Again, you have the equation. So if I just draw a schematic diagram, quick diagram here, that is the F, So from this part, that is XP. And this part, this is Y. Okay, and that's what we will calculate. Now, do you think you are ready for some calculation? No way, we have to do some preliminary calculations. You are right, you are right. You'll be ready on Wednesday, like fully ready. So today we will do some warm-up practice. So open your class example 8. We have two class examples there, 8A and 8B. So for this part, my plan is for each type of surface, we will do at least 2 practice problems so that you have a good amount of practice there. So open class example 8A. This is the simplest type of problem you can have for vertical plate. Now, one thing, this problem, I took that from your textbook, but they didn't use the formula method. Are you listening to me? Okay. So they used geometrical method in your book, but we will use the formula method in class. So if you're interested about other methods, you can look at the textbook. They solved each problem in 3 different ways. Okay. Can anyone read the class example 8A loudly and quickly? Read the class example 8A. Thank you very much. So they're saying there's a tank which is the rectangular. So and all the walls, they are verticals. Okay, and you have to find the force on the side wall and on the bottom. Do we know what type of liquid we have inside the tank?
Water.
We have water, okay, and I think that is the only given values here, like gamma, water. We are using SI system, so it will be 9810 Newton over meter cube, right? Ah, I wrote in the wrong place. Okay, it should be 9810. It should be 9810 Newton over meter cube. And we have to find force on this surface, F, A, B, C, D. Also force on what other surface? The bottom. So there is no name for the bottom, so I will just write down. Okay. So the F bottom, that will be kind of easy to find. Basically, the pressure of all the water that is actually on the bottom. What is the pressure here at water surface? P equals to? And what is the pressure here? P equals to? 3 gamma. Basically, that is the pressure on the bottom also, right? So you can work on that part very quickly, and we will do that very quickly. So let's start working on that. Are you done with the previous slide? Done, everyone? Okay, so this is the bottom plate. Can you give me the dimension for the bottom plate? What is the dimension?
1.5 meters.
1.5 meter to, okay. And I will try to draw a 3D. Okay. So here pressure is 0, here pressure is 3 gamma. So basically that is the pressure on each side, right? Okay. So if volume equals to P volume multiplied with area volume, right? So P volume is gamma times H, and the area is 1.5 times 2. Gamma is 9810 Newton over meter cube. What is H here? 3 meters, and 1.5 and 2 meters square. Finally, we have, what is the final answer with proper unit? So meter and meter square, that will be meter cube. Meter cube will get cancelled. Just newtons. And what is the number? Everyone got that? Okay. 88290. If I ask you to calculate that in kilonewton, that will be 8829 Newton, right? Sorry, kilonewton. Okay. Can you start working on the side wall? Just start working on that. You don't have to have the correct answer. So, are you done with this slide, everyone? Okay. So, side ABCD. This is the plate AD. What is the pressure here? 0, and here pressure. And what will be the distribution? What will be the shape of the load distribution here? Good. Okay. Okay. And we are trying to find is F, A, B, C, D, right? So what you will do now, what is the equation we derived a few minutes ago for pressure on, sorry, force on plane surface? Give me that. Gamma, then
H,
only H or H bar and okay. So find the gamma, find the H bar, find the A. We have 4 minutes, so I will spend these 4 minutes just to work on this part. So this is the plate. Just gamma is again same. What will be the H prime and what will be the A? you can find that to do that. What will be the gamma? Water. So gamma will be. What is the value of gamma? Yes, do that. And what will be the H prime? Read again. How did you get 1.5? Good. So we know this is the rectangular plate. And if you go to that static table here, for the rectangular shape, you will see that the centroid is actually halfway. And area will be what? Area will be what? Calculate that and tell me. Okay, give me the dimension of the ABCD plate. This one is 3. I already know that. 3 meters, right? What is that distance? Okay, so 9810. For finding the H prime, everyone, if anyone is struggling, the surface is rectangular, so you will go to this one. Okay, and you will see for this one, YC equals to H over 2, right? So that will be 3 over 2. Area is 3 multiplied with give me the answer very quickly.
88210.
Okay, this one. So you got answer what? 88?
200. Same as me.
Okay. Now we got the same answer, but this is just a coincidence. Okay. There is no meaning that you will always get the same force on bottom and the side also. Okay. So we will start to work on part B on Wednesday. Have a good day. We can't. I have one. Just. Oh, there is one, I guess, or I have.